The last video was a high-speed introduction to many of the layers of technology that make graphics tablets work. When it came time to do the full teardown and reverse engineering in that video, I focused on these tablets made by Huion. These tablets seem like good targets for creative reuse and modification since they're so simple and inexpensive. The Huion pens can be so simple partly because they require external power to operate. This one has a rechargeable battery. The Wacom pens, on the other hand, have this appealing feature. No batteries to recharge or replace, they're just powered entirely by the tablet itself. In this video, we'll be taking a closer look at the communications protocol used by Wacom tablets to power the corresponding pens and read their sensors back. I've changed the sensing setup somewhat from last time, with a slightly faster scope and some damping on the sense coil so that we can get a much better idea of what the waveform coming out of the Wacom tablet actually looks like. This is my current Intuos Pro tablet, and with this setup I can measure a carrier frequency of about 660 kHz. So in this test setup I have a simple analog filter that's just looking for these longer bursts so that I can help synchronize the oscilloscope, and that's on the second trace. And this top trace is just exactly what this coil is receiving. So if we zoom out much farther, we can see this pattern that repeats about every 7.5 milliseconds. That starts with a long burst of energy for about 1.5 milliseconds, and then many of these little bursts. And so actually, if I play with the sensor a little bit, I can tell that these are encoding pressure, and it looks like maybe right around here there's a bit that's always stuck in whatever that position is. If I push the top button, that bit changes. Interestingly, I don't see a change when I push the bottom button, even though clearly the computer is registering that button. It's possible that button has like a one-shot on it, so that maybe it only triggers for a single frame and I'm missing it on the oscilloscope. So this protocol seems to use this first millisecond and a half or so to indicate that a new packet is starting, but it probably also uses this to deliver enough energy to the pen so that the pen can operate for the duration of this packet. So it looks like each of these little blips is an opportunity to send back a 1 or a 0, and the pen indicates whether it's a 1 or a 0 by letting the coil kind of continue to oscillate or clamping down on the oscillation as soon as it can. So this definitely disproves my earlier guess that maybe the pen is sending its own location to the tablet. This is definitely a packet that only contains sensor readings. It looks like this is enough bits for pressure, but I don't see anything that would indicate tilt in here. So I'm also assuming that the tablet would be calculating tilt from the way the magnetic readings are shaped, rather than having any kind of tilt sensor in the pen. So Wacom has many pens that seem to use the same principle but are not really compatible with each other. I found this compatibility matrix that someone went to the trouble of making, and it looks like many of the recent pens are incompatible with each other. But there was a bit of a stretch of compatibility that includes the Graphire and the Bamboo Fun series. You also see these weird little wireless mice packaged with some Wacom tablets. One of these came with my old Bamboo Fun tablet. At the time I didn't think much of it. It seemed strictly less useful than every other mouse I had. The tablet makes a fairly bad mouse pad, so it got separated from the tablet itself, and when I gave the tablet to a friend, this mouse didn't go with it, and then I ended up finding it quite a while later. Recent Wacom gear like this Intuos pen is still pretty expensive, but you can find older Wacom tablets on the second-hand market for quite cheap. In order to investigate the signals between this mouse and the tablet, of course this mouse is not compatible with my new Wacom tablet, and I already gave away my old Wacom tablet, but it turns out that the tablets by themselves with no pen are quite cheap on eBay. So this Bamboo Fun tablet from eBay uses the same basic technique as the recent Intuos Pro, but it's a much more economical target for reverse engineering. The protocols seem pretty similar, mostly just differing in the modulation frequency and the number of bits per packet. The Bamboo Fun tablet uses a slightly different modulation frequency of 750 kHz, but if we zoom out and look at the larger scale protocol, it looks very similar to what we saw in the Intuos Pro. The overall pattern repeats about every 7.5 milliseconds. There's a little over 2 milliseconds spent just charging up the pen with power and indicating that this is the beginning of the packet. And then each of these following blips, just like we saw before, are opportunities for the pen to send back a 1 or a 0. We can see some of those bits change just by pressing buttons on the mouse. And just like with the Intuos, nothing here represents position. This is just transferring information from the buttons on the mouse back to the tablet. Just like we saw with the Huion tablets last time, these Wacom tablets operate a little differently depending on whether or not a pen is nearby. Here we can see a sort of scanning waveform as it's looking for a pen. Then when a pen, or in this case a mouse, moves into range, it changes to a different waveform where it's actively trying to power the pen and ask it for data. So this little Wacom mouse seemed like a really nice target for reverse engineering. It's not nearly as cramped as the Wacom pens, and whereas the pens are actually somewhat expensive still, I just had this mouse that I didn't need, and they're pretty easy to come by on eBay. This also interested me because, this is a relatively recent product, and you expect most things these days to have some kind of processor in them. And this has no microcontroller. All of these chips are discrete 74 series logic. So I found this design pretty interesting. It's not often that you see 74 series logic, and I suspect at the time this was designed, that was the most practical way of getting the ultra-low power consumption that this must have needed. The VCC rail on this is about 1.5 volts while it's operating, and these chips are specified to take, hundreds of microamps at most. So I reverse engineered this into a full schematic, since I think this is a pretty cool example of how you might still want to create something using discrete logic. These are the schematics I came up with. If you want a full copy, you can get them on my GitHub. At the highest level, you can break this circuit down into just two major components. There's an I/O component that handles communicating with the tablet, and then there's a sensor component that actually handles the buttons and wheel on this mouse. The communication circuit is responsible for extracting a little bit of power from this carrier wave, but also for using the timing information in order to figure out when each packet and each bit begins. The most complicated part of the circuit is actually just for converting the mouse wheel sensor's outputs into bits for scrolling up and down. That chip that's a little bit longer than all the others, that's a shift register, a 74LV165. This shift register has 8 inputs, P0 through P7. It's pretty much the simplest way you can convert parallel data into serial data. We can get a feel for how much of the device's functionality requires that binary packet by disabling it and then seeing what breaks. By shorting the output of the shift register to ground, I'm bypassing anything digital. All the bits going out of here will be 0. So with that output shorted, the mouse can still move and it's still detecting it, but none of the buttons work. So this tells me that maybe the portion of this mouse that's responsible for just moving around isn't digital at all. To examine how this works, we'll need a way of generating magnetic fields that change very abruptly. Surely the simplest way to generate a changing magnetic field in your device under test is just to throw a magnet at it. But for this to work, we'll need something about 100 times faster. Fortunately, electromagnets have no trouble going that quickly. To give us a nice repeatable source of magnetic impulses to work with, I have this other coil connected to a signal generator with a 1 kHz square wave. Alright. Now we have a reliable source of these magnetic impulses that change very quickly. This one rises in about a microsecond. As I insert the pen into the field, you can see two things change. The peak decreases a little, and this rippling pattern appears on the tail of the waveform. What we're seeing here is the pen absorbing some of the energy from that peak, then re-releasing it at a specific frequency. If we look closely at this ringing waveform, we can see the same frequency from earlier, 660 kHz. If I put the Huion pen from last time with its power turned off in the same field, you can see it also oscillates at 250 kHz, the same frequency we were seeing it transmit with. And just like we were seeing before, this changes based on pen pressure. The simplest circuit you can build that exhibits this behavior is just an inductor and a capacitor in parallel. You sometimes see this called an LC circuit or an LC tank. It acts a bit like an electric pendulum. The inductor transforms a changing magnetic field into an electric current. The capacitor then stores that electric potential, releasing it again as a current, which generates a magnetic field, and so on. The rate of this oscillation between magnetic and electric potential is controlled by both the inductance and the capacitance of the components. In this case, I'm changing the capacitance by turning a variable capacitor made from many partially overlapping plates. On this board, I'm using multiple capacitors in parallel just to achieve a more useful range of adjustment. But multiple capacitors in parallel act just like a single capacitor with a summed value. These LC oscillators are very sensitive to changes in component values. Just a small difference in capacitance can change the frequency by tens of kilohertz. So it's usually necessary to include some way of adjusting either the inductor or the capacitor so that the circuit efficiently operates at the frequency you want. It turns out that this tuned circuit is actually all you need for the Wacom tablet to detect the position of a pen. If this capacitor is adjusted too far out of the sweet spot, then the tablet doesn't detect this. But if it oscillates anywhere near 750 kHz, then the Wacom Bamboo Fun tablet detects this as a pin, and it reliably measures the position. Here we can see the LC tank circuit inside the mouse. The inductor is just the antenna coil. For the capacitor, they've built a sort of variable capacitor on the circuit board here that you can set using a soldering iron. C1 is always connected to the coil, and there's a spot for another capacitor, C2, that's not used in this design. Then all these other capacitors can be optionally connected via these solder bridges. During manufacturing, it looks like one of these jumpers, JP1, was cut and marked. Presumably this factory calibration was necessary to bring it close enough to its ideal resonant frequency of 750 kHz. Extracting DC power from this is pretty simple. C9 develops a DC bias that allows the coil signal to start floating between the two power rails. D1 is a 3-pin device with 2 Schottky diodes in series. Normally you would see a series diode setup like this in order to protect a circuit from transients. You would use this to shunt any unwanted energy that comes in either above or below the power rails into this capacitor. But in this case, that's exactly what we want. We want to take this AC signal and rectify it into some DC and store it in C12. And this circuit does that with very little voltage loss. Another very similar circuit is also capacitively coupled to the antenna, this time through C11. D2 is rectifying the AC into DC, and then it stores the resulting energy in C10. But this time the circuit's designed not to store very much energy, and to quickly leak it out through this resistor, R1. Here the goal isn't a steady power source, but a signal indicating when the carrier is being turned on and off. IC5 here is a Hex Inverter Chip, which is to say it has 6 little circuits that just know how to turn zeros into ones and vice versa. But in fact, these actually have a special feature, a Schmitt trigger input, which is to say that they're really good at cleaning up messy analog signals and turning them into nice clean digital signals. Here we can see the output of that simple peak detector circuit going into the inverter on pin 1, and coming out as a nice clean square wave. Then we can see an analog low-pass filter designed presumably to remove any quick glitches from that signal. You can see the rounded analog result of this low-pass filter being cleaned up by another hex inverter. So this signal that we're seeing on pin 4 of the inverter chip is actually used in a bunch of places, and I named this the carrier detect signal. It's actually used directly as a clock signal to clock out all the bits in that shift register that we saw earlier. But there's also another circuit specifically to detect this very long pulse at the beginning of the packet. This is a simple analog circuit that uses the voltage across C18 to keep track of the length of these carrier detect pulses. When carrier detect is low, C18 discharges quickly through diode D6. But when carrier detect is high, it's allowed to charge slowly through resistor R3. This analog signal shows up on pin 5 of the hex inverter, and then the cleaned up results are on pin 6. You can see my probing is actually causing this to glitch a little bit and make the packet start at the wrong place sometimes. This signal on pin 8 is the result of the long pulse detector, and I've been calling it load enable since it's used to trigger loading data into the shift register. This inverted version on pin 9 is also used elsewhere. The only other circuit attached directly to the antenna is this diode D3. If we look at the other side of that diode, we can see the signal that's being used to selectively damp the oscillations in the coil. When the signal is high, then not much current can flow through the diode, but when the signal is low, then quite a lot of the energy from the coil is shunted through diode D3 directly into ground. This control signal for the diode is calculated by a NAND gate using both the data from the shift register and another signal. On pin 9 we can see the output of that shift register going into the NAND gate. Next door on pin 10 we can see another analog waveform being generated based on the carrier detect signal. That NAND gate is set up so that the coil oscillations are only damped if both the data bit is 1 and this signal is high. The combination of D5 and C13 provides this rapid rise with kind of a soft knee here. Then after the carrier detect signal goes low, the combination of R4 and C13 provides this gradual slope so that the antenna actually continues to be clamped for a little while after the carrier signal is no longer being detected. I think this might help prevent oscillations. With the near-field I/O components all accounted for, we can explain the operation of this shift register a little more completely. If we look at the output of that shift register, we can see that a new bit starts every time the carrier pulse begins. If we look at pin 2 on the shift register, we can see that same carrier detect signal being used as a clock input. So every time a long pulse is detected at the beginning of the packet, this inverted load enable signal goes low, and that tells the shift register to reload its contents from the parallel inputs. Those 3 bits that we have tied to 1 and 0 permanently presumably indicate what kind of device this is to the tablet. The left, middle, and right mouse buttons are pretty simple, but we can see some power-saving features even here. It looks like they were quite concerned about keeping the power used by these pull-down resistors as low as possible. They have a very high value of 1 megaohm, and they're set up to only dissipate any power when the shift register is actively being loaded. Okay, well now we've explained everything except for this circuit, which generates these scroll up and scroll down signals that feed into the shift register. That quadrature decoder module is actually fairly complex. In fact, we have these 3 logic chips that are only necessary to condition the mouse wheel signal. This chip is for scrolling up, and this chip is for scrolling down. To see why this is all necessary, let's take a look at the quadrature signals that come out of the mouse wheel encoder. The wheel encoder in the mouse acts kind of like 2 buttons that press in sequence as you scroll the mouse. By looking at which edge arrives first, we can tell which direction the mouse is scrolling in. Quadrature is just the practice of using 2 signals that are 90 degrees out of phase with each other so that we can detect both the speed and the direction of this wheel motion. Even just looking at one of the quadrature signals and spinning the mouse wheel, we can start to see why this decoder circuit is necessary. With the magnetic packets on the top trace and one of the quadrature signals on the bottom trace, we can see that if we were only pulling this quadrature signal every time the tablet asked for an update, we'd be missing quite a lot of information. Both of the quadrature outputs have a little bit of RC filtering on them before they go into the decoder circuit. Alright, there's the quadrature signal, scrolling up, scrolling down. But now that we're inside the quadrature decoder, we can see that the A and B signals are being used a little differently. The A signal feeds the data input on all 4 of these flip-flops, which have the opportunity to sample that signal at different points in time. In this case, some of the flip-flops are being set up to sample when quadrature B goes high, and some are sampling when quadrature B goes low. This lets us build a logic circuit that makes determinations based on what state quadrature A is in anytime quadrature B changes. Well, here's quadrature A on top, and the somewhat cleaner-looking quadrature B on bottom that's been through a couple of inverters. And as long as I'm spinning the mouse wheel up, quadrature A will be in a high state whenever we see quadrature B have a positive edge. And if I spin the mouse wheel the other way, we can see the opposite phase relationship, and every time the scope triggers, quadrature A is low. The way these flip-flops are wired, they can be set to sample either the positive or the negative edge of quadrature B, using either this clock or this clock. By wiring either the inverting or the non-inverting output to this AND gate, you can choose what state to require quadrature A to be in when that edge happened. So this flip-flop is only detecting half of the scroll-up events, just the ones with a positive edge on quadrature B. Now this one's detecting the other half of those upward scrolling events on the negative edges. This NAND gate that's being used to generate the scroll down and the scroll up signals is actually kind of misleading, since the logical operation here is more like an OR. If we want to see a 1 on this scroll up output, it means we need to see a 0 on either of these inputs to the NAND gate. Since one of these flip-flops is inverted, that actually means that we want this flip-flop to be a 1, or this flip-flop to be a 0. This flip-flop is clocked when the B signal goes from 0 to 1, whereas this flip-flop is clocked when the B signal goes from 1 to 0. This circuit gives us a chance to detect upward scrolling on either edge of the quadrature B signal. And we're just looking for these kind of ghost outlines of the proper A signal. This bottom circuit is triggered by the same flip-flop states, but the clock edges here are reversed. Now we have half of our scroll down events, and here's the other half of our scroll down events, now on the falling edge of quadrature B. In addition to detecting the phase relationship between the 2 signals, this circuit also has the important job of latching the scroll signals until the next packet can go out to the tablet. Both of these circuits use a NOR gate to provide 2 different ways to reset both flip-flops into their inactive states. One of those reset inputs is wired up to the opposite scrolling direction, so scrolling up will immediately cancel a scroll down and vice versa. The other reset signal is generated by this circuit, which gives us a reset pulse as soon as we're finished loading the flip-flop. This circuit will convert a rising edge on this signal, or the falling edge on load enable, into a short pulse that both of these NOR gates can see as a reset for their corresponding flip-flops. There's our very brief reset. Well, there's the final scroll up signal. And there's scroll down. We can see that scroll up and scroll down stay latched until the next packet goes out to the tablet, ensuring that we don't miss any scrolling events. That's all I have for today. I hope you enjoyed this look into a neat little circuit that's powered by magnetic fields. Please let me know in the comments if you have any suggestions for other things you'd like to see, and be sure to subscribe if you want to keep up with the latest videos I release. Alright, thanks for watching. See you next time.